A very good evening to all the dear students. I am Anusree Sen from Kolkata. I have done my master's in physics with a specialization in astroparticle physics from St. Xavier's, Calcutta last year. So today I am going to teach you the topic that is gravitation and gravity, which is a very important chapter for standard 9 and 10 for CBSE and ICSE board. And along with that, it is very important chapter for 11th standard students for all types of boards. And it's a very important topic as well for the competitives. So before entering into the topic, at first I will like to share my experience how physics, what actually physics means. So physics is the laws of nature. Basically, physics is not all about problem solving or writing some question or answers. It is about the understanding the environment, understanding why and how the phenomena around us are getting happen. So when you are doing physics, when you are understanding physics, you are basically playing with the nature, with the laws of nature, and you are basically understanding, you are getting accustomed with this. So for understanding physics, for doing the problems, at first it is very important to be conceptually clear. And this is my first point on which I emphasize while teaching. So understanding the concept is the main pillar of success and main pillar of understanding the topics in depth. Number two is that when you are going through the topics, as in your class, class syllabus or for your board syllabus, you are having a lots of chapters. So while preparing for the topic, for a particular topic, then I personally prefer that go through the topic at first and clear all your doubts. And after that, make a short note by yourself only, which will surely help you for a short recall of the topics and the formulas. And after that, you just do the numericals from different competitive exams or from your previous year's questions. And along with that, you think about something interesting from a particular problem and try to solve that. In this way, I basically teach, and I basically think that this is the way how you should at first read something, then understand something, then you have to make it, understood by yourself very inherently, so that you can apply that in any problem. So the concept should be very clear. Along with that, you just note down the formulas and where and how you should apply that. That should be very clear. And after that, solve the problems and, get accustomed with the tricks and the concepts while you are using these formulas. So without further delay, let us jump into the topic that is gravitation and gravity. Here we are mainly going to emphasize on the topic which is Newton's laws of gravitation. As we all know that the fall of Apple first surprised Isaac Newton, and from that he has made some physics. He had experimentally observed some phenomena, and finally he has been able to give us the concept of gravitation and gravity in 1867. So before that even, it was 1687. So before that, actually what is gravitation and gravity is basically, as we know that, going uphill is more tiring than going downhill. Why is it so? Because when you are going upstairs, you are going against of a acceleration due to gravity. So you have to put more pressure, more force there. But when you are coming downstairs, then you are coming in the direction of gravity. That's why you need much less force in that case. So this is a very well-known example of our daily life. Along with that, when we see that raindrops are falling to the earth, it is falling downwards. Why? Because of the acceleration due to gravity, it is coming downwards. It's not going upwards. And there are lots of phenomena in our daily life where we feel that there is some attraction. The earth is attracting everything towards its center. So basically this gravitation says that everything attracts everything. That means every object can attract every other object surrounding it. But in reality, we cannot feel that because of our masses, because our mass are not much significant in that case. So this is something elaborately we will discuss later. So first to understand that the attraction is always present between each and every object, but we cannot realize or cannot visualize that due to our masses. So gravitation, why is it very important? Because from the very daily life phenomena to the astrophysical phenomena like planets, stars, galaxies, we can relate it. So this is a very universal and very fundamental law of physics, which does not need to be derived from any other kind of interactions or any other kind of forces. So here, as I have mentioned, that it is one of the universal force of attraction. And remember, this is the force of attraction. There is no force of repulsion in gravitation. It is the weakest force in the nature. As I have mentioned that, yeah, here every particle can attract every other particle surrounding it, but we cannot say this. Why? Because our masses are much less significant here. But if you consider the two magnets and bring them closer, you can see that they are attracting them very shortly. So magnetism, electromagnetism, or any other force like this are much stronger. But in the case of gravitational force, it is the weakest force. And always remember another point, that this is a long-range force. Why do we call this long range? Because the quantum of gravitational force, that is graviton, has no mass, but still it is feeling the force of attraction. So the points I have mentioned here, the first one, gravitational law is a universal law. It is a force of attraction, no repulsion is included. Number 3, it is the weakest force in the nature. That means for even massless particles, we can see this force. And number 4 is that this is a long range force, because the quantum of gravitation is the graviton. The well-known applications are mentioned in the slide. The objects present on the surface of Earth, like the cup that is kept on the table, do not levitate or float in the air because of the presence of gravitational force. The tides happen here due to gravity, the gravity between the Earth, Sun, and Moon. A number of daily activities like playing, sliding, jumping, running, everything is related to gravity. We cannot, just jump and go upstairs and do not get, it does not happen that we do not come down. So this is the gravity. The celestial objects, the celestial bodies present in the space revolve around our sun and rotate at their respective axis. There is a gravitation. If you do not have the gravitation between sun and earth, then how the earth is rotating in its axis constantly? Why it is not getting outside of the system? This is because of the gravity. So again, the water evaporating from the Earth's surface, which is also from gravity. The gases present in the sun do not leave the celestial body because of gravity. Fruits falling from trees, falling objects, the drinks poured in a glass stay to the base and do not rise up to the brim. If you put water in a glass, it do not come out. It does not happen like a water fountain. So it is because of the gravity. So on the Earth, all bodies have a weight or downward force of gravity proportional to their mass, which Earth's mass exerts on them. That means we have a weight in the Earth. We all are attracted with the Earth's gravitational pull. Gravity is measured by the acceleration that gives to freely falling objects. At Earth's surface, the acceleration of gravity is about 9.8 meters or 32 feet per second. Thus, for every second an object is in free fall, its speed increases by about 9.8 meters per second. This is a constant, the small g, acceleration due to gravity, and we will later derive the expression for this. Just understand that this 9.8 meter per second square, the value of acceleration due to gravity is constant. If you consider free fall, if there is no other obstruction or no other influence on the object, if it is only coming downwards due to the presence of gravity, then the only acceleration present on the body will be the acceleration due to gravity, which is small g, having the value 9.8 meter per second square in SI unit, which means that when there is a free fall of an object, for every second, the object in the free fall will experience an increase of about 9.8 meter per second in its speed. At the surface of the moon, the acceleration of a freely falling body is about 1.6 meters per second, again, per second square this is. So why it is so? Because when you are considering moon, the gravitational effect is getting changed. It is not the gravitation due to Earth. So the main point here I have been emphasized on is that gravitational pull is different for our Earth and different for our moon. Number 2, that is, if you consider free fall, then how the velocity is getting changed. These two are very important. The two questions may rise to your mind that then why moons does not fall to Earth? This is because the mass of moon and mass of Earth are much bigger. And in that case, the gravitational pull of Earth is much, small compared to the gravity. To the gravitational pull, the moon is revolving around its surface. So this is why the moon is not falling to the earth due to their masses. Does gravitation and gravity mean the same thing? No, actually not. The gravitation is something which is the phenomena, and gravity is something which is the force, because in latter cases, gravity or gravitational pull can be assumed as a field as well in general theory of relativity. So gravitation and gravity does not mean the same thing exactly. Now, coming to the main point, that is the Newton's laws of gravitation. Firstly, this Newton's laws of gravitation resembles the laws of electrostat, the Coulomb's laws of electrostat. But there are many other differences as well. The first thing, as I have mentioned, that Newton's laws of gravitation is only attractive in nature. But in electrostatics, the Coulomb's law is both attractive and repulsive. There are many other differences as well. So what does this gravitational law state? First, remember, this is a very universal law. That means wherever you apply this law, it will valid, right? Inside the earth or outside the earth. So what does it say? These laws of gravitation states that every object in the universe attracts every other object such that the force exerted will be proportional to the product of masses and inversely proportional to the square of the distance between them. This figure, this diagram shows how we are considering the phenomena. There we consider two masses, that is m1 and m2, and separated by a distance r. So gradually we can say that this m1 will exert a force on m2 as well as this m2 will exert a force on m1. This is the third law of Newton's law. So basically, here for the point masses, this term is very important, that is the point masses. What do you mean by point masses? Point masses mean if its dimension, if its geometrical dimension is much less compared to their separation. So, as we know that the Earth is huge, Sun is huge, but still we are applying Newton's laws of gravitation to them. Why? Because the separation between them is much larger compared to their dimensions, compared to the size. Therefore, we can apply the Newton's laws of gravitation in these cases. So, whenever you are thinking some object to be the point mass, that means the dimensions, the size are much less compared to their inter-separation. Is that clear? So, if we consider 2 point masses m1 and m2 and separate them by a distance r, then the gravitational pull between them will be directly proportional to the product of masses, that is the product m1 and m2, and will be inversely proportional to the distance square, that is 1 by r square. Because if you bring them closer, what will happen? The force of attraction will be much, and if you bring them much larger, if you bring them away from each other, the force of attraction will get loosened. So the laws are F proportional to m1, m2 and F proportional to 1 by r square. So as a whole, it is m1 proportional to m1, m2 by r square. Okay. So I have told you that this is a very universal law and this is an attractive law. The second point you should remember about this force is that this is the central force. This gravitational attractive force is a central force. What do you mean by central force? Central force is something for the force which is acting towards or away from a very fixed point. So if you are thinking that our Earth, which is rotating, so it is rotating around the sun, so the force between the earth and the sun is directly directed towards the line joining the centers of sun and earth. That means the force which is pointing towards or away to a particular point is called the central force. And in the context of central force, the angular momentum of the object or the point mass which we are considering for the system as a system will remain the constant. And along with that, what will happen, that the motion of the particle or the substance will be lying in the same plane. So these two are the corollary of the central force concept. And again, I have said that gravitational pull is a central force. So from this, when we will be entering to the Kepler's law, we can prove all these corollaries. That is, the angular momentum dl dt will be 0. The rate of change of angular momentum will be 0. That is, the angular momentum will be constant or conserved. Number 2, the motion of the particle will be confined to a plane. And the first one, that is, the force will be acted to a particular point away or towards it. That is, it will be a function of r. So these are the basic points about the central Newton's gravitation, laws of gravitation. And another point is very important, that is, it is independent of the medium. As in the Coulomb's law, there are permittivity or permeability for magnetostatics. So this medium dependence is not much importance in Newton's laws of gravitation. It is medium independent. Wherever you measure it, you can measure the laws of gravitation in water or in glass. Whatever be the medium you are measuring the force, the law will remain the same. So F equal to this law, F1 equal to F2. Actually, here we are considering only the magnitude of the forces, that is F1 and F2. If you consider them as a vector quantity and take their directions, then they will be oppositely directed to each other. That is, F1 will be minus of F2. So considering only the magnitude, F1 and F2 will be given as G M1 M2 by R square, where G, capital G, is the gravitational constant, universal gravitational constant. Okay, so as I have told you, this is a vector quantity F. So F1 will be equal to minus of F2. So how you will term this F1? How you will call this F1? Actually, you can call this F12. You can write it as F suffix 12. That will mean that the force on first object due to the second one, if you consider it F21, that will be the force on second object due to the first one. And F12 will be essentially equal to minus of F21, oppositely directed. So if I consider a system of n number of particles and we consider the gravitational law, then how you will summarize this formula? Okay, if you consider the system of I particles, then for each and every particle, for the ith particle, I minus 1 particle will interact with that object, that ith object, and you will get the gravitational loss, gravitational force. So basically it will be a vector sum of all the gravitational pull exerted by other I minus 1 objects on the ith object. So you will then consider the vector sum of the gravitational forces on that particular ith object due to other I minus 1th objects. That is the concept. Here I have given a demonstration, how the distance affect the Newton's laws of gravity. So here are a quick recap of the characteristics of the gravitational force, which is very important here. So conservative force, because of the gravitational force, the work done due to the gravitational force is 0. We can prove it later with the calculus, mathematical calculus itself. And as I have mentioned that this will be a vector sum, you can put a vector sign over the force here. And here I have shown the two masses, small m and capital M. You can see that small m is much smaller than capital M. So A12 is the acceleration of mass m due to the force of mass m2, capital M. And here again, A21 is the acceleration of this capital M due to the gravitational pull of small m. So basically, again, you can say that this A12 will be equal to minus of A21. Along with that, I will rather mention some points which are, you have to remember in the case of competitive exams. So first, if I consider this system, here I have told you that F12 equal to minus of F21. That means if you take the sum F12 plus F21, that will give 0. So the net force on the system will be 0. If I consider I number of particles, since then this will be true that the total sum Fi will be resulting into a 0 value. But you cannot say that A21 and A12 will be equal or their sum will be 0, because their masses are not same. So if you can say that F12 equal to minus F21, though you cannot say that A21 equal to minus of A12, right? And along with that, another point is very important. That is, if you take a center of mass of this system, then acceleration of the center of mass of the system will be essentially zero, which means that the velocity of the center of mass of the system will be a constant. And the main thing here is that the F net, the total force on the system, will be essentially zero. So here is the elaborating numerical on this. Okay, fine. From there, two things are very essential, which is not mentioned in the slide, since I'm telling, that is the unit of capital G, which you can find from the unit of F, mass and distance, and along with that its dimension. And remember the value of capital G, that is 6.673 into 10 to the power minus 11 in SI units. So if you are provided with two masses, that is M1 90 kg and M2 5.98 into 10 by 24 kg, and if you are asked to determine the force of attraction between this earth and the man who is standing at the sea level, then we can apply this law, F equal to GMM by R square, and finally we get this result. Now, if you put three masses, M1, M2 and M3, three having a mass, equal mass, that is 5 kg at the three vertices of a triangle, and if you are asked to find the resultant gravitational force on any one of the masses, then how you can do this? So here what we will do, that here we will consider this M1 as a test charge, on which we will consider this M3 and M2, I mean the force due to this M3 and M2. So by Newton's laws of gravitation, the force on mass M1 due to M2, that is this one, the force will be what? F12, which is given as G M1 M2 by R square, that is the side square, 0.25 square. For the third object, M13, this one, it's given as that 6.627 into 10 by minus 11 into 5 square by 0.25 square. Now, these are the two forces which are acting with their vectors, right? So when you are considering the resultant vector of these two forces, that means this capital F is a resultant of F13 and F12. You have to consider parallelogram law in vector addition. So as F12 and F13 are making an angle of 60 degree, as this is an equilateral triangle, so the resultant will be given as F12 square plus F13 square plus 2F12 into F13 cos of 60 degree, and hence you get the resultant force which is asked in the question. This is the resultant force, gravitational force on the mass M1. Now, another important question: if we're provided with two identical spheres whose masses are not given, and you are asked that how the force is depending on the radius, then how you can do this? Can you directly apply the GMM by R square? No, because you are not provided with the masses. In the mass, the radius dependence is also incorporated. So in that case, what is the way? So in that case, you just substitute mass as the product of volume and density. You give it as m equal to 4 by 3 pi r cube rho. Then you put that g into 4 by 3 pi r cube rho into 4 by 3 pi r cube rho and divide it with r square. And hence you get that the dependence of force on r, the distance of the radius, not the radius, you can say that, yeah, radius of each sphere. So that is r to the power 4. Here, the interseparation is supposed to be 2r, right? So in this figure, the direction of gravitational force on M1 due to M2 is along. If you are asked, then the answer will be, is it R1 or R2? No, this is R, small r only. Okay, so the force is along the direction of R. Another question which is very important for competitive type, that is, if a mass capital M is split into two parts, small m and capital M minus m, then which are then separated by a certain distance, then find the ratio of small m by capital M, which maximizes the gravitational force between them. So if you divide the masses in two parts, small m and capital M minus small m, then what happens? The force will be F equal to some constant, G, or I have taken it as scale, into M minus M in a bracket into small m by R square, where R is the separation between them. Now, if you want to maximize the force, what is the way? You have to take the first order derivative of the force with respect to small m and equalize it to 0. So df dm gives us m minus 2m equal to 0, which gives us small m by capital M is equal to 1 by 2. So this is a question asked in NEET. So these are the few problems I have discussed, and from this we can go into depth and again calculate the gravitational potential energy. From that, the variation of gravity, that is small g, with respect to height, depth, and along with the rotation of earth, and hence we can deduce the Kepler's law, and finally see how the satellites are moving and what are the significance of them. And then we can practice the numericals along with that. So up to this, the topic for today ends here. And a very warm thank you to all for being the listener. So thank you.